Welcome back. This is the second part of section 2.1, in which we are going to give some fundamental examples of differentiable and non-differentiable maps. But first, let us formulate two basic results about differentiability before we give counterexamples or examples. So first result says that differentiability at a point implies continuity at that point, and this is an expected result, as you know. Why? This is straightforward. Just write the condition of differentiability at A. So we approximate f by a linear map, f of A plus dfah plus a remainder. Now, the remainder, of course, tends to 0 as h tends to 0, and by continuity of dfa at 0, this also tends to 0, so the difference tends to 0, and therefore f is continuous at A. Okay, the next result concerns the conservation of differentiability under a change of norms. Okay, so if you have a map from an open subset of a normal space into another norm space, if on the source space we put another equivalent norm and on the target space we put another equivalent norm, does differentiability change? No, this is the result. It's the same and the same derivative. So when we replace the norms by equivalent norms, the differentiability is conserved and the derivative is conserved. It's the same derivative. Okay, this is not difficult. So we have now on E two norms, the original norm E sub E, and the equivalent norm sub 1, and on F we have the original norm sub F, and norm 2, which is equivalent. Okay, so in particular we have 4 inequalities, but I only need just 2. I need the fact that the original norm is bounded from above by a constant times norm 1, and the original norm of f is bounded from below by a constant times the second norm. Okay, so I want to prove the condition of differentiability at an arbitrary point A. So let epsilon be an arbitrary positive number, and write the condition now of differentiability with respect to the old norms. So this is just the meaning so there exists, but instead of epsilon, I take beta epsilon over alpha. Okay, so it's not really important, but in order to get in the new norms epsilon, I have to multiply by a constant here. So instead of epsilon in the definition of the condition of differentiability with respect to the old norms, instead of epsilon, take beta epsilon over alpha. Okay, so there exists a delta such that if norm of h in the old norm of h is less than delta, then this quantity is less than beta epsilon over alpha times the norm E of h. And now, as an exercise, you will find a number delta 1 such that if norm 1 of h is less than delta 1, then the same quantity in norm 2 is less than epsilon times norm 1 of h. Okay, and this precise, if you find such delta, then you would have proved that f is differentiable at A with derivative f prime of A. This is really not really straightforward. Okay. Okay. This is a very useful result actually, because it will permit us to use any norm you like, provided it's still equivalent to the original norm. Okay, now we give some fundamental examples. So, first result, also expected, that a constant map is C1 and its derivative is 0. So, this is really trivial because if f is constant, then f of a plus h is f of a. So, this is really 0. So, when we subtract the 0 operator, we get 0, and 0 is a small o of h. So, this is really trivial. Second result, also expected, if F is a linear bounded map, okay, so the domain here is U actually, is the whole space E. If F is linear and bounded from E to F, then of course it is of class C1, and its derivative is constant actually. So the derivative at every point is the map itself. Therefore, it doesn't depend on X, so it's constant. Okay, this is also trivial. Just the linearity of F implies that f of x plus h is f of x plus f of h. So when I do the difference, I get 0, and 0 is a small o of h. So this is and this is linear now in h, linear bounded in h. So the derivative at every x is f, okay, and therefore doesn't depend on x. So f prime is constant. Okay, this is really straightforward. Now, what about bilinear bounded maps? Okay, it's a bit more complicated. But also, if we have a bounded bilinear map from a product of two norm spaces E and F into a norm space G, then we claim that it's of course of class C1, and its derivative at a point, here a point is a couple actually, its derivative at the point x1, x2 in the increment h1, h2 is f of, so I replace the first variable by the first increment and the second variable by the second increment. So I get this formula. Okay. So if you like, it resembles the derivative of a product, if you like. Okay. So to simplify, we take the maximum norm on E times F, but as we know, we can take any other equivalent norm. For example, if it's easier for you to work with the sum of the components or the Euclidean norm, you can take it, but it's easier to work with the maximum norm. Okay, so we go back to the definition. So we write f of x1, x2 plus h1, h2. Okay, this is bilinearity actually implies that we can develop this. So it's like the product of a plus b, c plus d, right? So first we use the linearity with respect to the first variable and linearity with the second variable, and we get this expression. So this is the sum of four terms: f of x1, x2, f of h1, x2, f of x1, h2, plus f of the increment h1, h2. Okay. So I just do the difference. Okay. Now, okay, fine. Now, if you look at this term, f of h1, x2 plus f of x1, h2, this is actually, this is not bilinear. This is linear in the couple. Here we have to pay attention. There's a big difference between linear in a couple and bilinear. Okay. So this map as a function of h1 of the couple h1, h2, it's not linear in h1 because because it's a fine. There's another constant here. Okay, but if you add an increment to h1 and an increment to h2, we get the sum. Okay, so this map, as you may check, is linear in the couple. Okay, and not bilinear. And this will be my derivative. Okay, so it's just enough to prove that the remainder here is a small o of norm of h. Okay, and this is trivial because, and of course, boundedness is trivial, as you may check, because f is bounded. So continuity is conserved, if you like. So this will be my the Frechet derivative. So now, if you look at the remainder, f is bounded. So by definition, its norm, the norm of f of h1, h2 is less than the norm of f times the product of the norms of each component. So this is just the continuity of a bilinear map. And now each h1, if you took the maximum norm, the norm of h1 is less than the norm of h, right? Because it's a maximum. And similarly, norm of h2 is less than the norm of h. So we get this is less or equal than the norm of f times the norm of h squared, which is a big O of norm of h squared, which is of course a small o of the norm of h. So when we divide by norm of h, we get 0. So, and that's it. We are done. We found a bounded linear map, which is this bounded linear map in h1, h2 in the couple, such that we have this linear up to. So the remainder is a small o of h, and so this illustrates this condition of differentiability. So this is the second result. Okay, and more generally, we can generalize this to multilinear bounded maps. Same thing. We'll not write the proof. If you have a multilinear map in n variables, and of course it must be bounded. Of course, it's of course of class C1. I didn't say why this is of class C1. Actually, because of this. Because if you look at as a function of x1, x2, continuity of f implies continuity in x1 and x2. So this is you may prove that easily actually. Okay, so as a function of x1, x2, this continues in x1, x2. Okay, so the formula is the same. So just replace the first variable by h1 and add. So the second term is replace the second variable by h2 and so on. And lastly, you replace the last variable by h. So it's exactly the same thing, same proof, but it's a little bit cumbersome to write. Okay. Next result. It links our notion of differentiability with the existence of partial derivatives that you studied in calculus in first year. So now we specialize. We take E to be Rn, and we know that we can equip it with any norm because all norms on Rn are equivalent. So you choose the norm you like. And we take F to be R. Okay, so we have a function of n variables defined on some open subset U of Rn. And so this result states that differentiability at the point implies the existence of partial derivatives at that point, but the converse is not true. Okay, this is very important. Okay, it's not difficult. Okay, consider the canonical basis of Rn. So E1 is just 1, 0, 0, 0, E2, 0, 1, etc. So EI is we put 1 in at the ith place and 0 elsewhere. Okay, now by assumption we have this condition. So f of a plus h minus f of a minus the linearization is small o of h. So when I divide by h, I tend to 0. Now in particular but this is true for, okay, so in particular if you take h equal TEI. So since the norm of EI is 1, then the norm of h is just the absolute value of t. Okay, therefore h tends to 0 if and only if t tends to 0, right? So I can rewrite this in this way. The norm of the difference, instead of h, put TEI. And since here it's linear, so dfa TEI, I can put the t outside because by homogeneity. And here I get absolute t. Okay, now by homogeneity of the norm, this is just, I can put the t inside because here I'm dividing by a real number, not by h. I cannot put h inside here because h is not, it's a vector. So I don't know what does it mean vector over vector. But we can divide a vector by a real number. So I can put t inside the norm and I get this. And now I split it into two fractions, the ratio, Newton's ratio. And here I simplify by t. Okay. And I get this condition. And that's it. Now, if you look at this ratio, so this ratio has a limit as t tends to 0. And the limit is precisely the Fréchet derivative applied to the ith element of the basis, of the canonical basis. Okay. And okay, if you write this ratio in a more familiar way, what does it mean to add to A, which is A1, A2, AN, the vector TEI? So it's all the components are 0 except for the ith term. So it's equivalent to adding t to the ith component. So this is just the partial Newton's ratio. So here we give just the increment to the ith variable. And by definition, when this limit exists, it's equal to the partial derivative with respect to the ith variable. This is by definition. So the existence of this ratio, of this limit, actually implies the existence of each partial derivative. Okay, so we prove that Frechet differentiability, or if you like, linearization or linear approximation. So here, if you like, if you consider a function of several variables, here instead of a tangent line, you have the notion of tangent plane, if you like. So Frechet differentiability means precisely the existence of a tangent plane. And the existence of a tangent plane implies the existence of partial derivatives. But the converse, yeah. So here, just an example. What, in this case, what does it mean? How can we look at the Frechet derivative at the point? It's very easy, because now if we take just an arbitrary element, h in Rn, it's component h1, hn, and we apply the Frechet derivative to h. Now, since we have a basis e1, en, then we can expand h. So h is a linear combination of ei, where each hi is, well, this is by definition, actually. So I can write h as sigma of hi ei. Now, linearity tells me that I can put the sum outside, and I can put the hi outside. So I get sum of hi times the derivative applied to ei. But we saw that the derivative applied to ei is just the partial derivative of f. So this is just really a dot product of what we call the gradient of. The gradient is the vector of component, the partial derivative. So, so this is just the usual dot product between the gradient and the vector h. So this means that we can identify the Frechet derivative with the gradient. In principle, they are not the same, but they can be identified because dfa is just a linear map from Rn to R. So we know that it can be written as a dot product. Okay, so the slight difference, because this is a linear map and this is a vector. Okay, but we know that we can identify a linear map with the vector. Okay, which is a very particular case of Ridge theorem. So we can. So the Frechet derivative at the point A is just the gradient, if you like. So in simple terms. Okay. Now, why the converse is not true? And it's just enough to give a counterexample. So, and probably encountered it before. So take the function of two variables. So n equal 2. So f of xy is just xy over x squared plus y squared if xy is different from 0, 0 and 0 otherwise at 0. Okay. Now, we have to observe that by definition, if we put instead of y 0, what do you get? If x is different from 0, you get x times 0 over x squared plus 0 squared. So it's 0. And if x and y are both 0 there, then it's 0. So f of x 0 is 0 for every x. And similarly, f of 0y is 0 for every. So this follows from the definition. And therefore, when I consider Newton's ratio with respect to the first value, so I add an increment t here. So f of 0 plus t0 is just f of t0, which is 0. So the numerator is, and f of 0, 0 is 0. So I get 0 over t. So, and this has a limit 0. And similarly for the other one. So this precisely means that the partial derivative at 0, 0 exists and it's equal to 0. And same thing for the other partial derivative. So the partial derivative exists actually. And they exist everywhere. So here I just took at 0, 0 because at every point different from 0, 0, there's no problem. This is just the ratio of two differentiable functions, so there's no problem. So the only problem is at 0, actually. But is f the Frechet differentiable? Not at all, because it's not even continuous. Okay? So here's an example where we have partial derivatives, but we don't have Frechet differentiability. And you will encounter, of course, more such counterexamples in the exercise. Okay, and now a generalization of the previous result. Instead of taking a function of several variables, a scalar function of several variables, we can take what we call a vector field. So a vector field is just a function of several variables with several components, okay? And so if you denote the components by f1, fm, the variables x1, xn, then it's very easy to prove that f is differentiable at the point if and only if each component is differentiable at that point. And this is very easy to prove. I suggest that you write the proof by yourself. But don't worry, because we shall prove a more general result later. Okay, but it's very important to understand this case first. So differentiability of this vector field is equivalent to differentiability of all the components. And we know that the differentiability of all of each component implies the existence of partial derivatives. And we have now what we call the Jacobian matrix. The Jacobian matrix, how is it formed? In the first column, we take each component and differentiate with respect to the first variable. Second component with respect to the second variable, and last component with respect to, we cannot really interchange here the roles, okay, because otherwise you get the transpose of the matrix. So here, as you may easily check, the differential derivative can be identified because the differential derivative is a linear map from Rn to Rm. And we know that we can identify linear maps from Rn to Rm with their matrix in the canonical basis. So we can identify this differential derivative with what we call the Jacobian matrix. And it's not always squared, okay, because m may be different from n. So if you take m equal 1, actually, we just get one line, which is the gradient of f. Okay. And the last counterexample is generalize the fact that the absolute value is not differentiable at 0. But more generally, we can prove that the norm is never differentiable at 0. Okay, so this is an extension of this. So the first example of a non-differentiable function is just the absolute value. But pay attention, this f can be differentiable elsewhere, but at 0 it's never differentiable, no matter what kind of ingenious norm I take. Okay, the reason is very easy. So suppose that this function is differentiable at the origin. So therefore, I can go back to the definition and write 0 plus h in norm minus norm of 0, which is 0, minus the linearization is a small o of h. Okay. Now, this is true for all h small enough. So if I replace h by minus h, what do I get? I get norm of minus h, which is just norm of h. And here I get df0 of minus h, so I can put the minus outside and get plus df0 of h. And the small o of minus h doesn't change, the same thing. So we get these two identities. Norm of h minus its derivative at h is a small o of h, and norm of h plus the derivative is small o of h. So when I add these two, we get 2 norm of h is a small o of h. But of course, this is impossible because norm of h over norm of h doesn't tend to 0. So the norm is never differentiable at 0. Okay, and now I think I'll stop here in order to not make this video very long. And in the next and last video of this section, I will prove an important result about differentiability of the inverse function. So thank you for your attention and see you next time.